So this is called the fundamental theorem, part 1, at least in this book. In other books, it can be called fundamental theorem, part 2. Okay, because the fundamental theorem, the way I have known it, is f of b minus f of a when you're taking the integral. But this is kind of where that idea comes from. And so if you have a continuous function, then this thing, big f of x, implies that that's an antiderivative. Okay, the antiderivative of whatever's inside here, evaluated at x. Okay. Now Cameron asked why. So what it says is that this antiderivative is a function of whatever x is. Okay. And then if I take the derivative of the integral, I get out the original function, which is kind of weird. Okay, but I get out this is the antiderivative evaluated at x. Okay, so for instance, if you have some function f of t, so here it is. Here's f of t, and I go from a to x. Okay, depending on what x value, Cameron, you're the one that had a question on this, right? Depending on what x value I choose, right, the area under that curve is going to vary, right? That's why I can't just call this f of x. Plus, I would have nothing to plug in here for t, right? Because I can't call this f of x dx, because I can't plug in x into there. Yes, sir?
Did you say that one is f of t? Because you marked it as f of x.
Oh, yeah, that should really be f of t. Yeah. Yes, f of t. Yeah, and then when I plug in x, then I get out the value of the integral at that point x, right? And that point varies depending on what that value changes depending on where I go for x. And basically what you do is you take the antiderivative of whatever is in here, right? And then the derivative of that antiderivative is f of x, okay? And you don't have to worry about this thing right here. So this is kind of the important thing. You don't have to worry about this thing because what's the derivative? So if I take the antiderivative of this, if I took the antiderivative, I would get big f of x, right? Big f of x. But if I plug in a constant in, plus a constant, right? But if I plug in a constant in here where this is a constant, what's the derivative of a constant?
0.
0. That's why I don't have to worry about this the bottom number. Okay, so I'll do some examples and hopefully it'll make some sense. Don't think about too much theoretically, except this is saying the derivative of the antiderivative is a function of this number up here. When this number is a constant. Yes, sir.
So little f of x and big f of x, two separate functions.
Two different things. Yeah. Big f of x is the antiderivative of that function. Okay, and this is the derivative of the antiderivative. Okay, it's kind of weird. All right. Yes.
What if the function is continuous, but it like goes straight upwards?
Maybe it has vertical tangent.
Yeah.
And it still works. Okay? Still works. Yes, Robin.
But if you take the derivative of the antiderivative of the function, won't that just give you the original function?
It will give you the original function, yeah. So, but I'll show you kind of the way it works. Yes.
What's the difference between antiderivative and
What's the difference between an antiderivative and an integral? An integral is an indefinite. Antiderivative is also known as an indefinite integral, which we haven't really talked about yet. But an integral implies the area between. It's the area. It's a quantity. Okay.
the antiderivative is like the actual function?
Yeah, the antiderivative you use to evaluate the integral.
So if
okay?
you plugged in a value in the antiderivative, you would get the integral, basically?
Yes, you get the value
Yeah,
of
the value.
Yeah, the integral is the actual function. The value of that integral is when you plug in. Yeah.
Okay.
And the antiderivative is an indefinite integral, but we have a definite integral is a number. Okay, it's
Yeah.
where it's something where you about what you did on that quiz. What's the area underneath this curve, right?
Okay.
That's a definite integral. Okay. Okay. So these problems will seem really elementary when you look at them. So they'll give you something like this: find d dx of the integral. Find d dx from a to x. So let's not change it. Let's go from negative pi to x of cosine of t dt. Anyone know what that is? Doesn't this look scary? You will see something like this on an AP test, I guarantee you. And you go, oh my goodness, this is hard. What's the answer? The answer is just plain old cosine x. That's all it is. Okay. How did I get it? That's what the first fundamental theorem says. It says if you want to evaluate this function at x, the derivative of the antiderivative, all it is this. Okay? So all you have to do is plug in that x for the t. Okay? That's all you have to do. Now, where does that come from? What's the antiderivative of cosine of x? Sine of x. So what you don't want to do is take the antiderivative of that, which is sine of t, right, plus a constant, and then, no, it's a positive sign, right, because it's derivative of, yeah. And then you would subtract, so this is kind of the thing, sine of t plus c, and you would evaluate this one at x, right, and you would evaluate this one at negative pi, and subtract those two quantities using the fundamental theorem, the other fundamental theorem part. But what's the derivative of sine of x plus a constant? Cosine x, right? So if I took the derivative of this, right, I just get out cosine of x. What would I get if I took the derivative of this? What's the derivative of cosine of pi? 0, right? So that would just go away. So what I'd be left with is just that. So why bother going backwards and then going forwards when all you have to do is go forwards? You know what I mean? So that's the thing. Okay. Now it does get a little bit trickier because, well, I'm just going to do all these examples. What if I wanted to do d dx of the integral from 0 to x of 1 over 1 plus t squared dt? And you say, aha, that looks a lot like something. What does that look a lot like? Tangent, inverse tangent, right? And you could, yes, that is the derivative of inverse tangent of t. But why do that? All I have to do is take this and plug it in here, and I get 1 over 1 plus x squared, and I'm done. See? So you don't have to go backwards and then go forwards. You just have to go forwards. Okay? And this seems kind of dorky, but this leads to the idea of how you evaluate a definite integral. Okay? So the next type of problem where it gets a little bit tricky is if you have something other than just x up at the top. So what if I had y equals 1 to the x squared of sine of x, sine of t dt. What if I wanted to calculate that? What would I get?
Sine of x squared.
2 sine x.
Very close. Almost.
Oh, dang.
Almost.
Sine 2x.
What?
Sine 2x.
Not sine 2x. It'd be, so that this is equal to sine of x squared. Oops, sorry, it's not equal to. D, if they say find dy dx, not find the integral, but find dy dx, okay? It's not equal to sine. So this is not equal to sine. Dy dx is equal to sine of x squared. You just do plug in the x squared, but then you have to multiply by the derivative of x squared.
So is it sine x
To
squared?
times to it. Times to it. Okay? Which I would just write 2x times sine of x squared. So you have to apply the chain rule because, right? Because if I went backwards, right, the antiderivative of this would be negative cosine of t, right? And I plus c, and I want to evaluate that at x squared, right? And so first I plug in x squared, and then I go forward. So when I go forwards, what do I have to do when I go forwards?
Chain rule.
So you have to do the chain rule. So instead of going backwards and then taking the derivative of that and going forwards, I just have to know that when I plug that in, whatever this is, I have to multiply by its derivative up there. I don't have to do that if it's just plain old x, because the derivative of plain old x is what? 1, right? So you don't have to worry about it. Okay? Yes? And as long as this thing is a constant down here, it doesn't matter, you know, how you deal with that. Okay? What if you didn't have a constant down there?
You have another one at the bottom that comes up.
Let's do that one. Did you see that in your homework? Ah, that was the next problem I was going to do. So what Cameron asked, he said, what if you have something like this, where you have x at the bottom, add 3 at the top, and you have, say, x squared minus, not x squared, stop doing x squared, t squared minus 3t dt, like that. Okay? What if I had that and I said find d dx? You have to. Very good. So what Sam said, remember that rule that we learned about if you reverse the limits of integration, what happens to the sign of the integral? It turns negative. So I could rewrite this as d dx of negative. I could pull that negative outside. The negative of the integral from 3 to x of t squared minus 3t dt. And then I can plug in my x. So I get negative x squared. I could just multiply through the negative to begin with, which would have made my stuff easier. Negative x squared minus 3x, right? And then I would just distribute that through, which gives you 3x minus x squared, written in this form. X squared. Whoops. What? I meant 3x minus x squared. Write what you say, not what. Yes? Why do I flip it? Because I like positive. I don't like to read with a negative coefficient. Does that make sense? Make sense? Good. Questions? Now it gets a little bit more confusing. 2 more problems and then I'll be done. Okay? So what if, as in this example in the book, which is a good one, what if they want d dx, because d dx from 2x to x squared of 1 over 2 plus e to the t dt. And you said, oh, I thought this was going to be easy. Okay? So here's where you got to be kind of clever. So any integral, as long as this is a continuous function, which it is, I could break it up into intervals. And so I want to go from 2x to x squared, right? And it doesn't matter, I mean, so it says start at 2x and go to x squared, whatever that means. So if you have some integral, I could break it up, okay? If this is 2x and this is x squared, I might be going the reverse direction. I don't know, but as long as it's continuous, it doesn't matter. I could break this off at any point. So I could go from, so I want to find the function for finding the area between that curve and that axis, okay? And so, or if it's negative, I would, anyway, if it's negative, I find the value of that in. But I could stop at any point. I'm going to choose, I could stop at 5, but I could also stop at 0. And you don't know that.
How do you know x squared's after 2x? Because you can.
What? And in this case, you know that this is always positive, right? So 0, can I plug in any number in there? I can plug in any number there. It doesn't matter. Okay? It could be a negative number, it could be a positive number. But to make my life easy, I'm going to break this off at 0. So I could rewrite this as the integral, okay, of as the derivative of two integrals. The first one going from 2x to 0, and we'll just call it f of t for right now, instead of writing out the whole thing because I'm lazy. Plus the integral from 0 to x squared of f of t dt. Do you follow what I just did? Yes,
How do
sir.
you do it? 0 to negative 2x
Because 2x and x squared, because the domain is all real numbers. I can plug anything in there that I want to, okay? So I can plug, because I don't know what x is, right? So I just do 0 because it's easier. I don't have to worry. But I could put 10 in there, or negative 17.37, or whatever I want to. Yes? Because when I take the integral of that, it doesn't matter what's on the bottom. So what do I have to do to this to integrate it? Flip it and make it negative, right? So I'm going to rewrite this as the derivative, okay, of the integral, okay, the derivative of the integral from 0. I'm going to write this one first, okay? So it's going to be 0 to x squared of this thing, 1 over 2 plus e to the t dt. And I'm going to flip this and make it negative, minus the integral from 0 to 2x, same thing, right? 1 over 2 plus e to the t dt. And then I just evaluate those two things at their various points. So here, so notice this is 0. This could have been a 5, right? It could have been a 10. It doesn't matter what's on the bottom, because when I integrate, when I take the antiderivative and then take the derivative, the constant part is going to disappear, right? So I don't have to worry about that. So now I just plug in x squared, and I apply the chain rule. So this part, the derivative of this part is going to be, I'm going to skip a step, 2x over 2 plus e to the 2x. Do you guys see where that comes from? Because I plug in, not 2x, x squared, sorry. X squared. I take x squared and plug it in here, and then I multiply by the derivative of x squared, which is 2x. Yeah?
Yeah.
And then over here, I write 1 over, what's this part going to look like?
2 plus
Oh, what's on the top?
2.
2. Yeah, I mean, you don't have to do it in one step. 2 plus e to the what? 2x, and then you're done. Okay? And you can't combine these because these are in common denominators, right? So you're kind of done at that. Yes, sir.
how'd you get 2 on the top?
And I get 2 on the top, the derivative of 2x, right? Because I have to apply the chain rule. So I'm multiplying. I should have written it as 1 over 2, right? But I just skipped a step. And then you're done. Okay. We have to pause for that you're going to see. So it was at this point in the last class that I actually accidentally turned off the recorder, but I didn't do that. And this is a little bit confusing too, find a function, but it's easy, you just have to kind of know what to do. F of x with derivative, y equals f of x, with derivative dy dx equals tangent of x. That also satisfies no, it doesn't end there, okay? That also satisfies the condition f of 3 equals 5. F of 3 equals 5. So, let's first worry about this thing. What is a function whose derivative is tangent of x? We don't know one, right? We don't know one specifically, but we could cheat because I know an integral whose derivative is tangent of x. What's the integral whose derivative I can take to get tangent of x? No, you're thinking too hard. What's the integral? What's the integral of this? What's the derivative of this integral? Tangent of x, right? Okay. So what it's saying is, what can I take the derivative of to get that its derivative is tangent of x? Well, one thing I can take the derivative of is going from a constant up to x dt, right? So what would be the derivative of this? What would be the derivative of this? Tangent of x. But if I plug in 3 in here into tangent of x, right, what do I get out? Not 5, right? But one way I could remedy that is by putting I could take, so, or if I put a 3 down here, okay, what would be then if y equals this, and I want f of 3? What would f of 3 be in this case? If I plug in a 3 to there. F of 3 would be what? 0, right? Because the integral from 3 to 3 is 0. So what do I have to do to this function to make it such that f of 3 is equal to 5? I just add 5 to the end, you see? So if I add 5 to the end, not inside the derivative part, inside the integrand, not with this is called the integrand, not inside the integrand, but after I take the integral, if I just add 5 to it, I will get a function such that f of 3, right, is equal to 5. Is its derivative still tangent of x? Yes, okay? So that's one way to remedy that. Why would you ever want to use that? If you don't have an algebraic technique for finding the antiderivative, then you would have to do
It's
something.
3, so the integral from 3 to 3 is tangent.
It would,
dt.
the answer is just this right here, okay? Because it's not the integral from 3 to 3. You start at 3 because f of 3, this part would then turn to 0, right? And so f of 3 would be equal to 5, and its derivative would still be equal to tangent of x, you see? Yes, sir?
What if it's not 3 then? What if it's 2 or 1?
If this is 2 over here,
Well,
can you just change that number?
can you change that? Is that
Yeah, they just say, just change that. So if I did this, then f of 3 would no longer be 5, right? Because this thing wouldn't be 0. It's, right? So you have to, so there's a couple problems like that, and it's kind of, trying to get you to think. And that's the end. So your homework, which you can do, is page 295, Oh, no, I'm not sure. I got it wrong. Oh, it's easier than that. It's page 306. 1 through 25 odd. Look at how simple I kept it. Page 306.
Are those A through E?
Nope, just easy stuff. 1 through 25 odd. And the first 10 or so, or whatever, the first up until 19 is just the first part where you're plugging in just like those examples I did, and the last 2 or 3 are ones like this one. And that's it. And we're done here. I talked for 20